So unless otherwise stated, I forgot to record, G is 10 meters per second. We can assume that the potential energy just comes from gravity. And we get 2,500 joules. Again, you can use your formula sheet to figure this out. Okay, how much gravitational potential energy? Yeah. Would the person have if they were on the moon? There's still gravity on the moon. So let me look up that value. What's going to change for this problem? Gravitational acceleration is no longer 10. I think it's 1.6. It's about G on the moon is like 1.62 meters per second squared. Your math. So it's only about 1/8 as strong. So if you were on the moon, you'd weigh 1/8 as much. So if you so an 80-pound object on Earth would weigh about 10 pounds on the moon. I believe that's correct, something like that. So now we have a different G value. It's the same equation, we just use the, this is mass times G times H. Mass is still the same, that doesn't change. Our G, we now use 1.62 meters per second squared. And our height is still 5 meters. You'd only have 405 joules of energy. Alright. So a car, or let's just say a box has 5,000 joules of kinetic energy and is moving at 10 meters per second. How much mass does the box have? So a box has 5,000 joules of kinetic energy and is moving at 10 meters per second squared. How much mass does the box have? So how will we solve this? So this is dealing with kinetic energy. So we look at our formula sheet. Here's kinetic energy equations. And we are solving for mass, so we use this equation right here. So mass is equal to 2 times the kinetic energy divided by velocity squared. So 2 times 5,000 divided by 10 squared. What mass did y'all get? 100 kilograms. So 2 times 5,000 is 10,000. 10 squared is 100. These two zeros cancel out those two zeros, giving you 100. Everyone comfortable with word problems? The first. Alright. How much work is done by pushing a box, a 50 kilogram box, 5 meters with a force of 10 newtons? So what's something I told you about work? Do y'all remember? Look at your formula sheet at the units portion. So units, energy and work are measured in joules. Work can technically be measured in Newton meters, is an acceptable unit for work, but we sometimes just call it joules. So, but what I tell y'all about work, what must be true for work? Remember, force and distance traveled must be in same direction. So if you push a box forward, you're pushing forward on a box, and the box moves forward, that's the same direction. So work is equal to force times distance. This is our force, and this is our distance. This 50 kilograms doesn't matter. So our force is 10 newtons. Our distance is 5 meters. So that's 50 newton meters. Or you can just replace that as joules. Newton meters is acceptable. Also joules is acceptable too. Alright. Okay, you push a 50 kilogram box over a distance of 5 meters. It has an acceleration of 5 meters per second squared. How much work is done on the box? So we know the equation for work is equal to force times distance. 50 kilograms is what variable? Mass. 5 meters is going to be a distance. And 5 meters per second squared is a acceleration. Do y'all remember what force is equal to? So force is equal to, so remember that force is equal to mass times acceleration. The mass was 50 kilograms. The acceleration is 5 meters per second squared. So that's 250 newtons. So recall that we F equals ma. This is something that you'll have to memorize. We use it quite a lot in this class. So our force is 250 newtons. Our distance was 5 meters. And that should be 1,000 Newton meter. Or you could just put joules. I will accept either. So pay attention. I gave these two examples for two different reasons. In the previous example, the mass of the box isn't used because we're given force and distance. So we never used the 50 kilograms. In this example, I don't give you force anywhere. You have to recall that force is equal to mass times acceleration. So you can't just look at the numbers and start plugging them into a formula. You have to actually pay attention and actually work the problem out. A box is sliding across a frictionless floor at a speed of 10 meters per second. However, a distance of 5 meters, you push downward with 50 newtons of force. How much work was done on the box? So what's the answer? Yes. Why is the work 0? It's because you're pushing downward on a box that's moving to the right. You can think of the box going across the floor in this direction. Without any friction, it'll continue moving for all eternity, right? It'll never stop. And pushing down on the box would just push it into the floor, but without any friction on the floor, pushing downward would do nothing. If there was no friction and you were to go jump on a box, you wouldn't stop it. You just continue moving with the box. It will slow down due to conservation of momentum. You're adding mass to the box, your mass. But it would not actually slow down or stop. What makes it stop is friction. If you push down on a box, you're increasing the friction. You're increasing the contact between the floor and the box. You're increasing how much friction there is. But without any friction, pushing down on a moving object would not change it or do anything. So work is 0. It's also the reason why if the road is super wet and you were to slam on your brakes and lock up your tires, your car will continue moving forward and it won't slow you down hardly any, even though you slammed on the brakes. It's because the friction has reduced down to so little that your car is just going to keep moving forward and you're going to go off the road or slide into something. So I want to introduce elastic potential energy to you guys. I think everyone's good with gravitational potential energy and kinetic energy. Y'all seem to be comfortable with work. Work is simple as long as you remember to pay attention. So elastic potential energy. So suppose we had some sort of spring. Any of y'all ever play pinball? So if we were to compress the spring by some distance x, really compress it. So we compressed it back by some distance x. So compress the spring back by some distance x. We will be adding elastic potential energy to the spring. And it's done by this equation. The elastic potential energy, note the G here stands for elastic potential energy, is equal to 1/2 times some constant times the distance squared. So this is the spring constant. And this is distance compressed. This distance compressed could be the other way too. I say compressed. If you pulled the spring out, it would be no longer compressed, to be expanded. It's how much you move it. You can move it in either direction. You can either push on the spring and compress it backward, or you can pull on the spring and it'll do the same thing. Because what happens if you pull a spring out and you let go of it? It'll snap back. Or if you pull on a rubber band and you let go of it, it'll snap back. So this applies not only to springs, but rubber bands. This K depends on the material and shape of the spring. Every spring has a unique constant. So X is measured in meters. K is measured in newtons per meter. Newtons per meter. Because when you're multiplied by meter squared, one of this meter's going to disappear and you're going to get Newton meters. So let's do an example. Suppose we had a spring with a spring constant of 1,000 Newton meters. Usually the spring constant is going to be extremely large. Because remember, this is a meter. So how often do you compress a spring by? You usually compress it into centimeters. You take a spring and you do it. If you have a spring that can be compressed by a meter, that's very powerful. That's probably like the springs on an airplane when they land. Suppose we compress the spring by 1 centimeter. A centimeter is 0.01 meters. How much potential energy is stored in the spring? So remember that potential energy is 1/2 times the spring constant times however much distance you compressed it by. And we need X to be in meters, K in Newton meters to get potential energy in joules. So this is our K. And we're not going to use centimeters, we're going to use the meter version of this. So this is our X. So 1/2 times 1,000 Newton meters times 0.01 meters squared. I'm putting units in case you're curious how the units come out. So 1/2 times 1,000 is 500 Newton meters. 0.01 meters squared is 0.0001 square meters. It also, if you're typing this in the calculator, it'll put 1 e negative 4. This is the same thing as 1 times 10 to the negative 4, which is the same thing as 0.0001. These are all three the same numbers. But if you just put, yes. But when typing this in, you get 0.05 joules. So a very, very weak spring. Again, springs usually have a tremendous amount of, are very big K. I'm curious if I can actually look this up. Spring constant for spring in pen. If you're curious, so a common spring that we all have is the spring in our pen. Is that very strong? That's about 263 Newton meters. That spring has just enough energy that when you click it, it moves forward the needle and ink. So this is a very, very super weak spring. And remember, 1 joule of energy is the amount of energy required to lift an apple 1 meter into the air in 1 second. Obviously, the spring wouldn't be able to lift up an apple. You don't have to worry. I'm sticking to only gravitational potential energy. But we could all, in the diagrams, but let's do a conservation of energy problem. So we have a spring. We have a 0.05 kilogram marble. We bring this back. We compress the spring by, what's a good value? 0.03 meters, so 3 centimeters. So 3 centimeters would be this distance from here to here. I actually almost drew it to scale. So how fast would the marble be launched at if we had a spring rated at 10,000 Newton meters? And compress the spring by 3 centimeters, or 0.03 meters, and placed a 5 gram, or a 50 gram, which is the same thing as 0.05 kilogram, marble on it. So this is the before we will compress it down to this much, or afterwards we're going to have the marble being flying at some velocity. So I like doing my before and after. And to make it even better, let's list all of our constants. So here, so remember back when we created our original table, right? I began by listing I began by doing MGH, right? What was MGH for? Potential energy for gravitation. Now I'm going to be doing K and X, and then I'm going to have M and V. So these are the variables for kinetic energy. These are the variables for potential elastic energy. Again, I'm not going to make you do this, but I'm just showing you that it can be done. I then have kinetic energy, potential energy, and total mechanical energy. So at the beginning, we have 10,000 Newton meters. This is a constant. It's literally in the name, spring constant. At the very beginning, beforehand, we compressed the spring by 0.03 meters. After you let go of the spring, how much is it compressed by? 0. The mass of the marble is constant, 0.05 kilograms. Before I release the spring, how fast is the marble moving at? 0. So if it's moving at 0, what would be the kinetic energy? Alright. If it's not compressed by any, how much would the potential energy be? 0. And so we can solve for potential energy here. Or potential energy is just because of elastic. The height's not changing or anything. So that'd be 1/2 times K times X squared. You really don't need a table for this. This is too simple for to use a table on. You could just do straight up math. So we got 10,000 per K, and we got 0.03 squared here. And we come up with 150 joules. Total is the sum of these. And total, if there's no friction, we assume no friction unless stated otherwise, be the same. So the kinetic energy would be 150 joules. What you really need to know is the fact that all the potential energy will be converted into kinetic energy. So then, how do we get velocity from kinetic energy? That's really all you need to know. What was the total potential energy, and is it being converted all into kinetic? John, lift up your head. Put your mask on. Lift up your head. Pay attention. So all you really needed to know was that the potential energy is being converted into the kinetic energy. We know how to solve velocity from kinetic energy. Velocity is equal to 2 times the kinetic energy divided by mass. So I wouldn't do a table for this. I would solve for potential energy. So solve for potential energy and know that all the potential energy is being converted into kinetic energy. So the potential energy is converted into kinetic energy, which would be 2 times 150, divided by the mass. The mass is 0.05. This marble is going to be going at crazy speeds. Uh, 77.45, around that 6. meters per second. So when I release the spring, all the potential energy, so all the potential energy is converted into kinetic energy. So this potential energy will go into this equation. Yeah, I definitely wouldn't use a table for this. I would just recognize that fact. I don't have any homework problems doing this. It's not going to be on the test where you have to solve for velocity, I don't think. I might actually have something on the test, but I don't think so. Not that I can see. But let's say that you wanted to build a marble launcher. And you wanted the marble to get up to really crazy fast speeds. Or maybe you wanted to build a paintball gun that instead of so you know the airsoft guns that shoot little plastic beads. Let's say that you wanted to get it to actually shoot at a certain speed, and you don't want to use CO2, you just want to use a spring. What you can do is look up the spring constant for different springs, figure out how much you need to pull the spring back. So figure out how much the trigger will pull the spring back. When you release the trigger, it'll release the spring and push that little pellet at a certain speed. You can use this to actually build yourself an airsoft rifle or something. You can figure out what spring you need to do it, and start launching it. Do note that this speed right here. So remember, 80 joules of energy is enough to kill. A marble with this mass going at 77 meters per second is well enough to kill someone. Do not go to airsoft rifle that uses this. What they would look like is maybe we need to reduce the spring so it's only going 1 centimeter back and not 3. In my other physics class, my real physics class, we actually combine potential energy, gravitational potential energy, and have to work it out like this. Like we had just a roller coaster sliding down the hill. They have examples where a spring launches the roller coaster, and then it starts going down hills and moving. So really, there's nothing new when it comes to springs and elastic energy. You just need to know what K means. K refers to something called the spring constant, and X is the distance compressed. And all you do is you look up your table. So this could be distance compressed or distance stretched. This is a K constant or spring constant again. It could be a rubber band. By the way, for remote learners, here's the code word. So do y'all have any questions? I think my plan is I'm going to give out homework tomorrow. It's gonna, like, you can work on it in class. Like, I'll give it at the start of class. So it's gonna be in class work basically. But if you don't finish it in class, you can take it home to finish. Monday, I'm thinking test review and test Tuesday. So that's it for the day.